1958, the U.S. detonated a 9-kiloton nuclear device 500 meters below the Pacific near Inuiatak Atoll, and the results violated every pre-test prediction. That proved we don't fully understand what nuclear force does to the deep ocean. Science has since identified 6 cascading catastrophes a seafloor detonation could trigger, from atmospheric contamination to irreversible seismic chain reactions. Each escalates. Number 6 begins the moment the blast hits the surface. Number 6 begins with the most immediate escape route for nuclear contamination, a radioactive steam plume propelled directly into the sky. In 1946, the Baker shot at Bikini Atoll delivered a 23-kiloton blast just 27 meters below the lagoon surface. The result was a 600-meter-wide column of water and radioactive spray, hurling nearly 2 million tons of contaminated seawater into the air. Every ship in the target fleet was saturated with radiation, some so badly they were abandoned or sunk when decontamination failed. A modern detonation at a mid-ocean ridge would drive superheated radioactive steam into the upper troposphere, where jet stream winds, reaching up to 450 kilometers per hour, could sweep fallout across continents in days. The Castle Bravo test in 1954, with a 15 megaton yield, left fallout measurable in the United States, Europe, and Japan within 2 weeks. Fukushima's 2011 accident traced cesium-137 across the northern hemisphere in days. The ocean doesn't trap the radiation, it helps launch it worldwide. In the 5th place, the destruction of deep-sea hydrothermal vent ecosystems marks a loss that goes far beyond the immediate blast zone. In February 1977, the submersible Alvin descended to the Galapagos Rift and revealed thriving communities at 2,400 meters depth. Giant tube worms, clam beds, and dense microbial mats, all powered by chemosynthesis rather than sunlight. These organisms form the foundation of a food web that is unique to the deep ocean, anchored to the chemical gradients created by hot, mineral-rich fluids seeping from the Earth's crust. Inner Ridge now catalogs over 700 active or inferred vent fields worldwide, but each site is an isolated oasis, fixed, unable to escape a shock wave or the sudden collapse of their chemical environment. A nuclear detonation near a mid-ocean ridge would obliterate not just the visible life, but also the delicate chemical conditions that sustain it. Recovery is measured in decades or centuries, and many species remain undescribed, their biological and chemical potential lost before it is even understood. The true cost is not just local extinction, but the permanent erasure of evolutionary experiments that have unfolded in the dark for millions of years. Number 4 brings the threat of methane clathrate destabilization, a tipping point where a nuclear detonation could transform from a local disaster into a global climate crisis. Beneath the world's continental margins, starting at depths of 300 to 500 meters, lie vast reserves of methane hydrate, ice-like compounds locking methane within seafloor sediments. The U.S. Geological Survey estimates that these deposits hold around 1,800 gigatons of carbon, surpassing the total in all known conventional fossil fuels. A deep-sea nuclear blast does more than just vaporize rock. It unleashes a triple assault of heat, pressure shock, and seismic disturbance, each capable of pushing these hydrates past their stability threshold. When released, methane is a climate accelerant, roughly 80 times more potent than carbon dioxide over a 20-year span. The geological record offers a stark warning. During the Paleocene-Eocene thermal maximum, a sudden carbon release, likely from destabilized hydrates, drove global temperatures up by as much as 8 degrees Celsius, wiped out up to half of deep-sea foraminifera species, and left the planet struggling to recover for 200,000 years. In this scenario, a single explosion could trigger a feedback loop, turning a momentary act into a centuries-long climate upheaval. Number 3 on this list, radioactive contamination of the thermohaline circulation, marks a shift from immediate disaster to a slow-moving planetary inheritance. The thermohaline circulation, often called the global ocean conveyor, takes about 1,000 years to complete a full circuit. Deep water forms in the North Atlantic and Southern Ocean, sinking and carrying dissolved materials, including contaminants across the abyss. If a nuclear device were detonated near one of these deep water formation zones, radioactive isotopes like cesium-137, strontium-90, and plutonium-239 would be injected directly into this interior ocean system. Cesium-137 and strontium-90 have half-lives around 30 years, but plutonium-239 persists for over 24,000 years. After the Castle Bravo and Bikini Atoll tests, these isotopes were detected in Pacific samples for decades, but those releases were mostly at the surface, where mixing and dilution are relatively rapid. In the deep ocean, the story changes. Contaminants become enclosed within the slowest, most persistent circulation on Earth. It takes about 150 years for deep North Atlantic water to reach the North Pacific, and nearly a millennium for a complete turnover. Cleanup is not just difficult, it becomes almost inconceivable. A single detonation could leave a radioactive fingerprint in the deep sea, traceable for centuries, moving silently through a system that regulates global climate and marine life. The danger here is not just the longevity of the isotopes, but the durability of the pathway itself, a contamination event that outlasts generations, quietly cycling through the heart of the planet's largest living system. Number 2 brings the countdown to the threshold of sudden, mechanical devastation, a submarine landslide and the specter of a mega tsunami. When a nuclear detonation strikes a pre-stressed continental margin, it doesn't just vaporize rock. The shockwave can destabilize millions of cubic meters of sediment, turning the seafloor itself into a projectile. History offers a chilling analog. On July 9, 1958, a magnitude 7.8 earthquake on Alaska's Fairweather Fault sent 30 million cubic meters of rock crashing into Lituya Bay. The resulting wave climbed 524 meters up the valley walls, the highest run-up ever recorded. While the bay's narrow geometry amplified the effect, the lesson is clear. Sudden mass displacement at the water's edge can unleash forces that defy intuition. Modern modeling extends this threat to a global scale. In 2001, geophysicists Stephen Ward and Simon Day simulated a volcanic flank collapse at Cumbre Vieja in the Canary Islands. Their model projected initial wave heights up to 900 meters at the source, with waves exceeding 25 meters reaching the eastern seaboard of North America. The 2004 Indian Ocean tsunami, triggered by a magnitude 9.1 earthquake and 15 meters of seafloor displacement across 1,200 kilometers, killed approximately 227,000 people, proof that a wave born in the deep can cross ocean basins in hours, with catastrophic results. Submarine landslides are not rare. Continental margins worldwide preserve deposits of ancient slides, each a silent record of past instability. In deep water, a displacement wave can travel up to 800 kilometers per hour, nearly invisible until it enters shallower coastal zones, where it rises without warning. Unlike radiological contamination or climate feedbacks, this consequence unfolds at human speed, measured in minutes, not centuries, making it the first on this list, capable of rapid transoceanic destruction. And finally, in first place, seismic cascade stands as the most catastrophic outcome, not simply for its immediate violence, but for its power to unlock every other disaster in a single coordinated chain. The world's mid-ocean ridges, the Mid-Atlantic Ridge, East Pacific Rise, and Indian Ocean Ridge, are already under relentless tectonic tension, their crustal plates locked and primed for movement. When a nuclear detonation is placed directly into these stressed fault networks, the coupling of explosive energy into solid rock becomes far more efficient than in water or air. Historical benchmarks offer a stark warning. A 1 megaton underground detonation has produced seismic waves equivalent to a magnitude 6.4 earthquake, a force capable of fracturing crust and propagating stress over vast distances. The Soviet Semipalatinsk test site recorded triggered seismicity on nearby faults after large underground blasts, confirming that even a single shock can tip a fault system past its breaking point. But the danger does not end with a single rupture. Coulomb stress transfer, a well-documented phenomenon in earthquake science, means that one fault failure can load adjacent faults, sometimes needing only a nudge to begin slipping in sequence. The 2004 Indian Ocean earthquake sequence stands as a modern example. A magnitude 9.1 rupture propagated over 1,200 kilometers, with smaller precursor events cascading into one of the deadliest tsunamis in recorded history. In the context of a seafloor nuclear detonation, the initial seismic impulse could ripple through the global fault network, unfolding over hours or days, and activating every other catastrophe described in this countdown, lofting radioactive plumes, destroying vent ecosystems, destabilizing methane clathrates, contaminating deep ocean circulation, and triggering submarine landslides or mega tsunamis all at once. This scenario ranks first for a simple reason: maximum connectivity, maximum system coupling, and the clearest path to planetary-scale irreversible change. Yet, despite the stakes, no government has published a comprehensive model of what a deep sea floor nuclear detonation would truly unleash. The 1963 Partial Test Ban Treaty ended underwater nuclear testing before modern oceanography revealed the complexity of hydrothermal vents, methane hydrates, and tectonic coupling. As of 2026, the United States and China have signed but not ratified the Comprehensive Nuclear Test Ban Treaty, leaving the world's most consequential scenario unmodeled and unregulated. The gap between what is known and what is at risk remains the most unsettling legacy of the nuclear age. Across all 6 scenarios, one pattern emerges. The ocean floor is not just a passive target, but a vast, interconnected system where a single human act can trigger consequences beyond prediction or control. When nuclear force meets planetary complexity, the true danger is how little we still understand.